So in my last lecture, I introduced the components of the data path. So we need components to build the CPU, and some of these components are combinational elements, as shown in this slide. For example, we need the ALU. Okay, the ALU is a combinational circuit. So basically, it does not really have, it's combinational because it does not really have any memory inside the ALU. And the output depends basically on the inputs, just on the inputs. So I talked about this slide last time, but let me just take a small pause here and talk about the 301 midterm exam. I'm still grading it. I did not really finish grading the midterm exam, so inshallah the grade will be before Tuesday. Maybe by tomorrow, inshallah, I will finish everything. I'm halfway through. I finished grading the first three questions in the midterm exam across all the students. I still have question 4 and question 5. Okay, so expect the grades, if not tonight, by tomorrow, inshallah. Okay, that's about the midterm exam. Back to this slide here. So I talked the last time about the components. So we have seen that some of these are combinational elements. We'll use a lot of multiplexers. This is not exactly the symbol which is shown here for multiplexer, which is shown in textbooks. So I'm using this symbol here in this slide because just to make the drawing so simple when I draw the multiplexers in the data path. So the multiplexer here has two inputs, input 0, input 1, and it has one output. And these inputs and outputs can be multiple bits, not just a single bit. It is actually multiple bits. Here, because we have only two data inputs, 0 and 1, there is one select input. The extender, I talked about it last time, which is used to extend a 16-bit immediate into 32 bits. Now, this is needed because both inputs to the ALU are 32 bits, so we need to extend before we can, let us say, add, or we can do a logic operation inside the ALU. Now, in addition to these, we have storage elements. I have the program counter. It is a register. Notice how the clock is connected to the PC. We need the memories. We need two memories, one for instruction and one for data. So the instruction memory will store all the instructions of a program. The data memory is going to store all the data of a given program. And these are implemented typically today in a modern CPU using caches, cache memory. So the instruction memory is nothing but an instruction cache, and the data memory is a data cache. But I will be talking about cache memory later, okay, in the semester, okay, not today. So I'm going to assume then that these are like simple memories. You provide the address of an instruction, you get the data. You get the data is an instruction. Okay, so in the case of instruction memory, you provide the address, you get the instruction at the output of the instruction memory. In the case of data memory, you provide the address, you get the data at the output. Now, this is if you are reading the data memory. If you are writing the data memory, you provide the address and the data as input to the data memory. Now, there are two control signals here, memory read and memory write, which are used to control the operation of the data memory. And finally, here I have the register file. Okay, so these are called storage elements because I can use them to store, okay, to store data, okay, or to store, in the case of the instruction memory, I can store the program instructions, or in the case of the data memory, I can store the program data. Okay, so this is why they are called storage elements. Now, I have more details about these components in the next few slides. So let us go into these details. So let me start first with the register element. So the register, we have studied the register. Okay, you remember the 202 course. This is very similar to the D-type flip-flop. But rather than storing it just a single bit, in the case of the D-type flip-flop, we store just one bit. we need to store n bits. So this is why it's called register, because we can use it to store n bits. So notice here that my data in consists of n bits. Let me use my highlighter. So here n is the number of input bits to the register, and what we are storing n bits inside the register. So think about it as consisting of n flip-flops inside the register element. So this is my data input. Now the value that you are storing currently inside the register appears on its output. So notice that my output here is also n bits. This is data out. So data out is the current state of the register. This is the value that we are storing inside the register. It appears on its output. Now, if you want to write the register, okay, we need a write enable. So the write enable here is used to enable the writing of the register. Okay, so if this write enable equal to 0, then we don't write anything into the register. So first we have to enable the writing, and then the writing will happen at the edge of the clock. Okay, so we call it edge triggered clocking. This is the clocking methodology that we are going to use, okay, for all the registers. So the change in the state of the register will appear at the edge of the clock. So whenever we would like to update a register, we update it at the edge of the clock. So this is why we are using D-type flip-flops, not latches, flip-flops, because in the case of a flip-flop, we change the value at the edge of the clock. Okay. Now this is if write enable is 1. If write enable is 0, then in this case there is no change in the state of the register, and therefore nothing is written inside the register if we are disabling the writing of the register. So this is the importance of write enable. So the clock is important to indicate that when, okay, when do we update, okay, at what moment in time we update the state of the register, and this will happen at the edge of the clock. And write enable is used to control whether to write or not to write the register. Is this clear? Okay, so this is just one register, and we can have many of these inside the CPU. Okay, so if I would like to build a register file, remember that in the case of the MIPS CPU, we have 31 registers because R0 is always 0. So we don't really need a register for R0. We need the registers for R1 to R31. So these are 31 registers, and each register consists of 32 bits. So we have 31 registers multiplied by 32 bits. This is the size of the register file. This is how many bits we are storing inside the register file. Now, in the case of a register file, we have many inputs. We have here RA, we have RB, and we have RW. Now, notice that these are only 5 bits. So notice that I'm drawing here 5, okay, on top of the wire, indicating that these are 5 wires. Okay, so these are 5-bit inputs. So the 5-bit RA is going to specify the 5-bit register. So when I specify RA, I'm specifying which register to read inside the register file. So 5 bits, because we have 32 registers. In fact, R0, okay, can be read inside the register file, but it's not implemented as a register. It's hardwired to 0. So we can read from R0 to R31. So this is why we are using 5 bits for RA. RB will be my second source register, and RW will be my destination register. So we're going to write always to RW. So we're going to read 2 registers, RA and RB, and we're going to write 1, which is RW. Now, whenever we would like to read a register, its value is going to appear on, so if I would like to read, let us say RA, its value will be available on bus A. So notice that bus A here is my output bus, okay, and therefore it's the value of register R8. So the value is going to appear on bus A, and bus A consists of 32 bits because each register consists of 32 bits. Now, the value of register RB will be available on bus B. So this is my second output bus. So we have two output buses here, bus A and bus B, because we can read two registers, okay, at the same time during the same clock cycle. Now, in order to write, yes, تفضل Omar. Yes. Omar?
So, yes.
Yes.
So the bus is the value, but the 5 bits, are they only the...
we specify the address of the register or the number of the register. Only the address or the number, because the address is nothing but a number between 0 and 31.
Yes, exactly.
So you specify which registers. Okay, you can read two, RA and RB. So you can read two, and you specify their addresses on RA and RB. So these are just 5-bit addresses or just 5-bit numbers from 0 to 31. And the values will be available on bus A and bus B. Now, if you would like to read R0, then you will get the number 0 on bus A or bus B. If you would like to read the same register twice, for example, if I would like to read register 1, then you specify R1, just specify the number 1 in binary, 5-bit number here, just in binary. So you specify 1 on RA and 1 on RB. So the value of R1 will be available on bus A and bus B. So this way you can read the same register twice. Okay. Now that's for reading. So you can read any two registers. You can even read the same register twice. If you provide its number on RA and RB, you are going to read the same register twice. Okay, that might be useful in some instructions. For example, if I would like to add R1 plus R1, if I would like to double the value of R1, okay, I might read, for example, R1 twice. Okay, so depending on the instruction, of course. And its value will be available on bus A and bus B. So remember that bus A is the value of register RA, and bus B is the value of register RB, and any two registers can be read inside this register file. If you want to write a register, then you have to specify that which register to write. So this will be RW. It is a 5-bit number that will specify that which register to write. And the data that you would like to write becomes an input. So here I have bus W, which is 32 bits. Now this is my input data. So my input data, the value that I would like to write inside the register RW will be provided as an input to the register file. Now, in order to enable the writing of the register file, I have this register write control signal that will enable the writing of the register file. If register write is 0, then nothing is written, even though I might have data here at the input. If register write equal to 0, then we write nothing. We don't update any register in the register file. And the writing will happen at the edge of the clock. So if register write is equal to 1, if we are enabling the writing of the register file, then we are going to write RW, and the data will be available on bus W, and the writing will take place at the edge of the clock. Remember that we have the clock here as an input. The clock is very important. It is used to synchronize the write operation to indicate that when we update the register file. Okay, is this clear? Okay, so for reading, we don't really need the clock. So if I would like to read two registers, RA and RB, I don't really need the clock. So the clock input is not used for reading. You can read at any time. As long as we have the value of RA and the value of RB, we can actually read two registers, and their values will be available on bus A and bus B. So for reading, there is no need for a clock. You can read at any time. But for writing, only when you would like to write, then in this case we use the clock, because you have to indicate when to write. Okay, so that's the importance of the clock. So the clock is used to synchronize the write operation. So I just would like to make sure that you understand this point, because the clock is used only for writing, not for reading. Okay.
Dictor,
Further.
can you just give us an example? Because the idea is in my mind, but it's not 100%.
I'm going to show you the
understand.
details. Yeah, so this is the basically the symbol of the register file as a component. But we can go into the details, okay, of the register file. Maybe this will be clearer. So when you look at the details of the register file, when you would like to build a register file, you can build it using registers. Okay, so here we have R1 to R31. Notice that there is no R0 because you don't store anything in R0. R0 is always 0. It is hardwired to 0. So notice that here for R0, I'm showing here the number 0. Right, that's the constant. So basically, you can just wire the ground. You can just connect it to the ground. So the wire is connected to ground, and the ground is always 0. Okay, so there is no register here for R0 because, again, we cannot really store any value inside R0. It's hardwired to 0. So we only have 31 registers from R1 to R31, as I mentioned previously. Now, if I would like to read, let me explain here the concept of reading. So here I have bus A, and here I have bus B, and bus A is the value of one of these registers. You can read R1 to R31, or it can actually be even 0. Okay, if you are reading, say, R0. Now, there is no register R0, but you can actually have the value 0 available on bus A. So for reading, you can actually have the value 0. Now, so how do we read? Now, we specify RA. Now, RA here is just a 5-bit number, which is in binary. And it's from 0 to 31. We know that in 5 bits, you can represent 32 values, right? From 0 to 31. So depending on the value of RA, you can read any one of these registers. We have here R1 to R31. So I'm going to use a decoder. Okay. Now remember the decoder from the 202 course. It's very important to remember these topics because we are going to use them now to build the register file. I'm going to use these as components in my CPU. So we have to understand actually the meaning of these at a high level. So notice that I'm not even using gates here. I'm just using decoders, registers, and so on. We're going to use multiplexers. And also I'm using tri-state buffers. I'm going to explain the tri-state buffer in more detail in the next slide. So what the decoder does, remember the decoder? Can someone explain me to the decoder? Okay, I don't want to explain everything. I want you to explain to me now. So what is the decoder? What is the decoder? I need to hear it from you. I need just to make sure that you remember, okay, what's the decoder? Remember that, okay, when you take a course, any course, okay, whether it's in COE or ICS, okay, so, and you take the final exam, the course does not really end at the final exam. Okay, so what you have taken in this course will be important for future courses. So if you study for a course only and you try to forget everything after finishing the final exam, this is not good. So you have to keep whatever you have learned in this course because it's needed, okay, for other courses. So this is why I said the background, okay, in the 202 course is very useful here, because we needed to actually build the CPU. So now you tell me what is a decoder. Yeah, I'm ready. I'm waiting. You have a few seconds. Yes, تفضل خالد.
The decoder decodes the value of the input and output. All the output will be 0 except for example, if the output is 5. All the output bits will be 0 except the bit 5 will be 1.
Excellent, excellent. That's all what I need to know. Okay. So remember that the decoder will take, this is a binary decoder. Okay. So its input is a binary number. Now RA can be from 0 to 31. So this decoder, if it has a 5-bit input, we have 2 to the power 5. We have 32 outputs. That's the decoder, right? So one of its outputs will be a 1, and all the remaining outputs will be zeros. That's the most important thing about the decoder. That's what you need to remember about the decoder. Now, this is very useful. It's very useful for building a register file. So now, for example, if the value of RA is 2, okay? So if it is 2, then output 2. So here we have 32 outputs for the decoder, which are numbered from 0 to 31. So let me use here my pen tool, okay? Just to clarify to you that we have 32 wires at the output of the decoder. So I need to use my pen tool and just to, hopefully I can actually just write clearly here. Let me see. Okay. So this is my pen tool. So now, if you look here at the output of the decoder, we have 32 outputs. So this is output 0. This is output 1. Okay, this is output 2. And this is output 31. Okay, can you see my handwriting? Can you see it? Okay, good. So you can see that we have 32 outputs from 0 to 31. Okay, so I'm drawing it like this. So this is output 0. This is 0, sorry, here. This is 1. Okay. So now suppose that here is my input here RA is equal to 2. That's actually 2 for RA. Then this output 2 here will be equal to 1. So this actually output will be equal to 1. So therefore this will be 1. And all the remaining outputs will be zeros, right? So when you actually have this, so this tri-state buffer will be enabled and all the other ones will be disabled. So these are disabled and except one tri-state buffer because one output will be enabled and all the remaining outputs are disabled. So now when we enable this tri-state buffer here for the output 2, this means that the output of R2 will be available, will be connected to bus A. So the tri-state buffer, what it does is going to connect its, so the output becomes the input only when the tri-state buffer is enabled. And otherwise, if it is disabled, then in this case, its output will be high impedance state. Let me talk about the tri-state buffer. This is shown here in this slide. The tri-state buffer. So the tri-state buffer, the idea of the tri-state buffer, it allows multiple sources to drive a single bus. Notice that here in this slide, we have 32 of these. If you would like one for output 0, one for output 1, notice that here we have 32 outputs numbered from 0 to 31. So this tri-state buffer will be enabled. If RA equal to 0, then we are going to enable this top, okay, tri-state buffer, and therefore bus A will be 0. It will be the constant 0. Okay. If RA is equal to 1, we are going to enable the next tri-state buffer, and therefore bus A will be R1. So here I'm connecting here multiple inputs. So we have here R1, R2, the output of all of these registers, including 0. We are all connecting them to the same bus A. So the importance of this tri-state buffer, it's like a switch. Okay, it is just a switch. If enable is equal to 1, then this switch will be closed and data out becomes data in. So we say that the tri-state buffer is enabled. On the other hand, if enable equal to 0, then this will be an open switch. And we say that the output is in the high impedance state. What it means, high impedance, it means that the output here, data out, is disconnected, okay, from data in. So it's not connected to data in. So the current cannot really pass through That's the meaning of high impedance, because the current cannot really pass through, and therefore the output is just like a floating wire. It's not connected to the input. Now you can use, let us say, two tri-state buffers to implement, and an inverter to implement a multiplexer. Suppose I would like to implement, let us say I would like to build a multiplexer. So this multiplexer has two data inputs, data 0 and data 1. It has a select input. So if select equal to 0, okay, if select is equal to 0, we are going to enable, so this inverter, okay, is connected to the top tri-state buffer. So the output of the inverter will be equal to 1. So if select equal to 0, the upper, okay, tri-state buffer will be enabled, whereas the one which is at the bottom will be disabled, and therefore the output here will be data 0. So we're connecting data 0 to the output. Whereas if select is equal to 1, we're going to enable the lower, okay, tri-state buffer if select is equal to 1, while the upper one will be disabled. So only one of these tri-state buffers will be enabled and the other one will be disabled. And therefore the output will be data 1. That's if select is equal to 1. So therefore we can use two tri-state buffers with an inverter. The inverter is very important so that we can enable exactly one of the tri-state buffers, because we cannot enable both of them at the same time. We cannot really connect data 0 and data 1 to the output at the same time. That actually will cause a short circuit inside the circuit, circuit. So therefore we don't really want to allow a short circuit and the high current. This will damage the circuit and it will damage the gates. It will burn the gates. Okay, when we have a short circuit, a high current output. Okay, so that will not be good. So only one of the tri-state buffers will be enabled and the other one will be disabled, and the output can be equal to either data 0 or data 1, depending on my select input. So we are building here a multiplexer. In this example, I'm building a 2-to-1 multiplexer. It has two data inputs, and select can select actually what is my output. It's either output is data 0 or data 1 according to the value of select. Is this clear? This is the meaning. This is the meaning of the tri-state buffer. So the output data out is equal to data in when it is enabled, and data out is in the high impedance state when it is disabled, when the enable input is equal to 0. That's actually what we need in order to be able to connect two inputs to the same output. Right. So this is called actually wired output. So if you look here and back in this slide, the details of the register file, back to this slide. So notice that, let me clean it up again. So notice that I'm connecting all of these registers, the outputs of all of these registers, R1, R2, all the way to R31 through tri-state buffers. All of them are connected to the same bus A. So notice that how I'm actually connecting all of them to the same bus A. I cannot connect them directly. Why? Because you cannot actually have a 1 and a 0 on the same bus at the same time, because the values of these registers can be different, right? So if, for example, the value of a bit inside R1 is a 1 and the other one is 0, okay, then these will be conflicting. You cannot really connect them. You cannot just wire them to the same bus A. Okay, this will cause a short circuit. It will cause a high current, okay, to move from the 1 to the 0, because 1 is connected to the power supply and 0 is connected to ground. So electrically, this will cause a short circuit. So the only way to do this is using tri-state buffers. So the tri-state buffers, as long as you enable exactly one of them and the other ones are disconnected, are disabled, okay, then in this case, you are connecting only one, the output of one of these registers to the bus A. So as I said, if RA here is equal to 2, this is my pen tool again. So if the value of RA is equal to 2, this is my example, okay, because you asked for an example. If RA is equal to 2 in binary, it's just a 5-bit number, then this tri-state buffer will be enabled. So this output will be equal to 1, and therefore, so this tri-state buffer here is enabled, right? And therefore, the value on bus A is the value of R2. So basically, we are connecting this 32-bit output of R2 to bus A. So we get the value of R2 on bus A. Is this clear?
Yes, yes.
Yes.
Okay. Now, that's actually how we can read. This is how we can read, because we take the output of the register and we provide on bus A, so we are reading. So this has nothing to do with the clock. As long as we have a valid value for RA, we can read one of these registers. If I would like to read R0, there is no register R0 here. I can actually enable this tri-state buffer. So I can actually get the constant 0 available on bus A. Remember that here the constant 0, all the 32 wires are connected to ground. That's it. There is no register. These are connected to ground directly. That actually is the constant 0. I can do exactly the same thing in the case of bus B. So this bus B here, you can actually use RB to read a different register. So for example, if RB here is equal to 31, okay, then I'm going to enable this tri-state buffer. So this will be 1. So this is actually will be 1. So this output here will be equal to 1. And therefore, all the other outputs will be zeros. And bus B will be the value of R31. So in fact, you can read any two registers at the same time. By providing RA and RB, you can read any two registers at the same time. Right. So if you look at all of this structure here, which is shown, all of this structure, you have a decoder, you have 32 tri-state buffers. Okay, one connected to ground, which is the constant 0, and the other ones are connected to the outputs of R1 to R31. So this is like a large multiplexer. This is a big multiplexer implemented using decoder and tri-state buffers. It has 32 inputs and it has one output. The output is bus B. So think about the decoder, and the tri-state buffers here are implementing a large multiplexer, a 32 to 1 multiplexer. So this multiplexer has 32 inputs. Okay, we have 0, this be constant 0. And we have R1 to R31, so these are 32 in total. And we have the output is bus B. And this is controlled by RB. So RB here is going to select, okay, which register to read and have its value on bus B. And also we have done it also for bus A. If you look at also this entire structure here, this big structure here, this is also another multiplexer. Okay, this is actually also another multiplexer for bus A. So we have like two multiplexers, okay, 32 to 1 multiplexers, but I'm implementing them using decoders and tri-state buffers. So I can read now any two registers from the register file. I can read according to RA and RB. So this is for reading. Okay, this is for reading. Let me talk about writing. How do we write the register file? I'm going to clean it up again. So let me use here erase all ink. If I would like to write, I'm going to use, let me show you here my highlighter. I'm going to have here, okay, bus W. So my data exists on bus W. Now notice that this bus W consists of 32 wires. So a bus is nothing but wires, okay? 32 wires, that actually is my bus. Because my data consists of 32 bits. Okay, notice that my bus W is connected to the inputs. So notice that bus W appears at the input of R1. So it's connected to the input of R1, of R2, and R31. You can only write these 31 registers. You cannot really write R0. So this is why it's not connected. There is no R0 because you cannot write it. It cannot be written. Right. So therefore, you can see that bus W is connected to the inputs of all of these registers at the same time. But we're not going to write all of them. We're going to write only one of them. Correct? We are going to only write one register. So therefore, this RW here is going to specify which register to write. So again, RW consists of 5 bits. It's going to be decoded. We have actually 32 outputs. Okay, so we have it from R0 to R31. So I can here have output 0, output 1, up to 2, and output 2, up to output 31. So we have all of these outputs. Output 0, okay, which is for R0. R0 does not exist. It's not used. So this output here is discarded. So if you want to write to R0, nothing is written. Okay. If you want to write R1, okay, so for example, if RW is equal to 1, we are going to enable this output here. This output will be enabled, and all of these other ones will be disabled, will be zeros. So if RW is equal to 1, let me just write 1 here. Suppose I would like to write, let us say, register R1. So this RW will be equal to 1. Okay, so we are going to write this register R1. So the output 1 here will be 1. And we need to end it with register write. So this register write, sorry. So this register write must also be enabled. So this will enable the writing of R1. So if both of them are 1 and 1, notice that I'm using an AND gate here, then the write enable will be equal to 1, indicating that we are going to enable the writing of R1. Now the output of the decoder will be all zeros everywhere. So therefore we have 0, okay, for write enable R2, for write enable R31. All of these will be disabled. Now the writing will happen at the edge of the clock. Notice that the clock is connected to all of these registers so that we can write any of these. But one of them is enabled. Notice that write enable is just 1 for one of these registers, and it is 0 for all the other ones. So we enable the writing of one of these, and therefore at the edge of the clock, the writing will take place. Okay, so therefore here we can write exactly one of these registers. Okay, is this clear? So these are the details of the register file. So this is how it looks from the inside. And now we understand that writing, we have to wait for the clock. We have to enable the writing. Of course, we write only one register, depending, of course, on the value of RW. Okay. Right. So in fact, we can read and write the same register. Yani, for example, if I would like to read, okay, and write, suppose that RA is equal to 2. Again here. So suppose that here RA is equal to 2 and RW is also equal to 2. Okay. I'm going to clean up, erase this here. Okay. So in this example, then if RA is equal to 2 and RW is equal to 2, notice that we read. So the value here of bus A will be the value of R2. So the value on bus A will be the value of R2. That will be the old value on R2, which is available at the output of the register. So notice that we do the reading before we do the writing. So we read first the value of R2. Now we can use it, for example, in some kind of a computation by an instruction. And then if I would like to write R2, so this will happen at the end of the clock cycle, at the edge of the clock. This is why the importance of timing the write operation. Then in this case, we are going to enable the writing. So here the write enable of R2 will be equal to 1. So we are going to write the value of R2. This will happen at the edge of the clock. So for example, this can be at the end of the clock cycle. So at the beginning of the clock cycle, we can read the value of R2. We can use it. We can do some kind of computation. And then at the end of the clock cycle, I can write R2. So the value will be available on bus W. This will be the new value of R2, and the R2 will be updated at the edge of the clock. All right, so these are the details of the register file. Any question about this?
So, Victor, for reading, we don't need a clock, right?
Yes, right. We don't need the clock.
Okay.
All right. So so let me talk here about how we can build an ALU, a multi-function ALU, which is shown in this slide. We need a component. The ALU is also a very important component. Okay, so I can use the ALU for addition, for subtraction. I can use it for a logic operation like AND, OR, NOR, and XOR. And notice here that I have a logic unit. Okay, and notice that here my logic operation, we can have like a variety of operations. For arithmetic, we need actually addition and subtraction. I can use the same adder to do addition and subtraction. Already we have studied the ALU in the 202 course. I'm just here showing to you how we can build. It's called a multi-function ALU because it can execute multiple operations, multiple functions. So the ALU is essential to compute the result of a given computation. Notice that here my inputs A and B are 32 bits. So if I would like to add, I'm going to use 0 for addition here. So this is actually used to control the operation of the ALU. So when you XOR B with 0, you get B, and therefore the result will be A plus B. Notice that C0 will be equal to 0, so it's going to be A plus B. In the case of subtraction, I'm going to use 1 for subtraction. So therefore, when you XOR B, every bit of B with 1, you get B prime. You get the 1's complement of B. But then you here have C0 equal to 1. So this will be A plus B prime, which is the 1's complement of B plus 1. So B prime plus 1, this will be the 2's complement of B. So A plus the 2's complement of B will be A minus B. So therefore, we have calculated A minus B at the output of this adder. So this is subtraction. So the same adder is used for addition and for subtraction. I have a logic unit. Okay, so this logic unit can do AND, it can do OR, it can do XOR. I can invert, okay, the OR, it becomes NOR, using this inverter here. Now I need a multiplexer. Notice the multiplexers, how they are used, because I need to select, okay, the output of this ALU. So I can do all of these in parallel at the same time. Okay, so I can do the AND, the OR, and the XOR at the same time in parallel, but I need to select one of them. So I use this multiplexer here to select here my final output. It will be available at the output of this multiplexer. So multiplexers are very useful. Okay, they are used for selection. I have here this is a 4-to-1 multiplexer. So because here I'm controlling it with 2 select, you notice that I have 2 select inputs. Sorry, 0, 0, 0, 1, 1, 0, and 1, 1. So these are numbered from 0 to 3 in decimal. I also have a shifter here on top. I can actually use it to implement a shift operation. But in the case of a shift operation, I only need a 5-bit shift amount. So here I have my data that consists of 32 bits and my 5-bit shift amount. So the shifter is going to shift by any number of bits. So this is not like a sequential, this is not really a shift register. This is a combinational circuit. You see that actually everything here inside this slide is a pure combinational circuit. So you provide the data, you provide the shift amount, and you get here the data. The output of the shifter, the output of the shifter will be the shifted value. So there is no register, there is no memory inside this shifter. This is not a shift register that we have studied in the 202 course. No, this is a combinational circuit that does the compute the shifted output. So if you provide here the data as input, the 5-bit shift amount. Also, you can provide the shift operation. Yeah, and you can use shift left logical, shift right logical, shift right arithmetic, or even a rotate. You can also use the shifter to do a rotate operation. And the shifter is going to produce its output. You can use the final ALU selection using this output multiplexer. This is for ALU selection. It is actually also controlled by 2 bits. You can select the output of the shifter. If you have a shift operator, shift operation, you can select the output, the input 0 here. So the ALU result is the output of this multiplexer. It can be the output of the shifter. Okay, if the ALU selection is 0, 0, you select this input 0, or you can say set less than. Now, in the case of set less than, you don't need a comparator for that. You can do subtraction. And then when you do a subtraction, you can check the sign. The sign bit here is the most significant bit of the result. So when you calculate A minus B, if A is less than B, then A minus B should be negative, right? So in the case of set less than, all what you need to do is just check the sign bit. But because you can actually have overflow, you can detect overflow based on the last two carries. This can be easily detected by the adder. The adder here can output overflow. So we have two cases. Either we have the sign is negative, or you have the sign equal to 0 and there is overflow. The meaning of overflow, it means you got the incorrect sign. The sign is supposed to be negative, but you are getting it positive because you have overflow. So if in these two cases, you can say that A is less than B. Okay, so here the sign is negative, but it turns out to be 0 because you had overflow, or you have no overflow and the sign is equal to 1. So you can actually XOR these two if they are actually the sign is equal to 1 and there is no overflow. So you have 1, 0, or you have 0, 1. So this is not but XOR gate, in fact. And then you can actually extend it here with 0. So either you get 0 or 1. In the case of set less, then you get 0 or 1. And this is the ALU result. So it's either true or false. You can actually take the output of the adder in the case of arithmetic. So we take here output 2. And finally, in the case of logic, you take here output 3. So basically, you can have many different operations, functions, which are implemented inside the ALU. Okay, is this clear? Now, the set less than is interesting. Why? Because you see, I did it in a clever way without the need of using here a less than, without using a comparator. You can use a comparator, but this is signed less than, not unsigned. Okay, this is SLT, not SLTU. Okay, so this is for signed integers. So you can actually calculate A minus B and you can check the sign bit. But because you can actually have overflow in the case of signed arithmetic, you can have overflow. So there are two cases. Okay, so either you have the sign is equal to 1 without overflow, so you have the correct negative sign, or you have overflow, which is 1, and you have the wrong sign, which is 0. In both cases, A is less than B. So in both cases, so this is why we need to XOR. I need to draw a XOR gate, but this is the same thing as putting not equal. So this not equal here indicates that the sign is not equal to overflow. So either you have 1, 0, or you have 0, 1. In both cases, you have A is less than B. Remember that the output of this is just 0 or 1. So this is why it has to be extended. It has to be extended. So you get the final output here as 32 bits, the ALU result. Remember that set less than is going to produce just a single bit, either 0 or 1, but we extend it to 32 bits because the ALU result is always 32 bits. Is this clear? That's actually how we can build a multifunction ALU. We know how to build an adder, right? We have studied that. This can be a ripple carry adder, or we can use some kind of a fast adder. Okay, so there are designs of fast adders, okay, that do not allow the carry to propagate, and therefore they can reduce the delay inside the adder. The ripple carry adder is the simplest to implement, but the drawback of the ripple carry adder is that it is slow because the carry has to propagate through all the bits, and therefore the delay is going to increase as we reach the most significant bit. Remember the ripple carry adder that we have studied in the 202 course? Okay, so that's important. That's the adder. Now, how about the shifter here? Now, this shifter is interesting. Now, these are just the AND, OR, and XOR gates. These are really simple. Now, notice that my inputs here are 32 bits. It means that this adder is 32 bits. And it consists of 32 full adders. Inside this adder here, we have 32 full adders, but I'm not going to draw all of them. Okay. Now, if you look at the AND gate here, I'm drawing it as an AND gate, but these are 32 AND gates because we have the inputs are 32 bits. So we have to end. This is bitwise ending. Every bit of A is ended with every bit of B. This OR is 32 OR gates. This XOR is multiplied by 32. So this is not just a single gate. These are 32 and 32 OR, 32 XOR, 32 inverters, okay? And the XOR here at the B input, this is actually for the adder, when we XOR every bit of B with the arithmetic operation, with the same while. The shifter is interesting. It's actually explained in the next 3 slides here. These are the details of the shifter. I'm going to skip these slides. If you are actually interested, you can go through these. I'm showing here how you can shift to the right. Okay, you can actually have arithmetic shift, logical shift, how you can shift to the left, or even how to rotate. It's very interesting, and it's implemented with multiplexers and an extender. So this is a pure combinational logic. It has no register in it. Okay, there is no memory. It's a pure combinational. So I'm explaining the details of the shifter, okay, in these 3 slides. Okay. So you can actually go through these things and understand the shifter, how it works. It's all done using multiplexers. That is a shifter by any number of bits from 0 to 31. And it can produce its result, okay, after going through these 5 multiplexers, you get the result very quickly at the output of this shifter. Okay, so it can be done in one cycle. In one cycle, you can shift by any number of bits. And if you would like to shift by 10 bits, by 20 bits, even by 31 bits, it can be done in one cycle. We also need instruction and data memories. Okay, so we need an instruction memory, which is used to store the instructions of a given program. And we need a data memory to which is used to store the data. Okay, so for example, if we have data in memory, we are going to store it in this special memory, which is called data memory. In the case of the instruction memory, we provide the address. So the address will be 32 bits. Okay, because this is a 32-bit architecture. So we're going to use 32 bits here for the address of the instruction. Now, because the instructions are aligned in memory, they are 4 bytes and they are aligned in memory. So all the instructions are 4 bytes in length. And because they are also aligned, the least significant 2 bits of the address will be 0 and 0. So the address is always a multiple of 4, and the least significant 2 bits will be 0, 0. So you specify the address, you get the instruction at the output of the instruction memory. The instruction, you can see here, it is 32 bits. So the address is 32 bits and the instruction itself is 32 bits. In the case of the data memory, we need to read, we need to write the data memory. So in the case of the instruction memory, we don't write the instructions, we always read them. In the case of the data memory, we have 2 control signals here, memory read and memory write. So these are used to control the data memory. We specify the address, which is 32 bits. So if I would like to read, I only need the address. You specify the address, you get the data out. This will be the output of the data memory. This is in the case of reading. In the case of writing, we specify the address and the data. Notice that the data now is an input to the data memory. So this will be the case when I would like to write the data memory in the case of a store instruction. Now the reading can take place at any time, but for writing, I need the clock. So the clock indicates when the write will take place. It's going to synchronize the write operation, and therefore the write will take place at the edge of the clock. Mushtaba?
Doctor, is the data memory an array of flip-flops, or
Yeah,
it is more complicated?
Well, it's not like flip-flops. It will be like static RAM. Okay, so the implementation of the memory will be static RAM. In fact, I will talk about this later in great details. So the instruction memory and data memory are usually kept small inside the CPU, and this is different from the main memory. The main memory is a different type of technology, which is called dynamic RAM. I'll talk about memory technology later. So we're going to replace the instruction memory and data memory with caches. So these are implemented today using static RAM, and they are implemented as caches. So I will talk about cache memory in details, okay, toward the end of the semester. But for the time being, think about it like a block of static RAM. It's a random access memory. You provide the address, you get the instruction at the output, or you get the data at the output. So we need 2 memories, one for instruction and one for data. Now, the separation of the instruction from the data is good because it allows us to address the instruction and the data memories at the same time during the same cycle. That's why we separate them inside the CPU. And this is well known as a Harvard architecture. So it goes back to decades ago when it was suggested that the instruction and data memories should be separated into two different memories, whereas the main memory is just one memory which contains both the instructions and the data. Okay, so these are not like flip-flops. Okay, these are static RAM, so the implementation is slightly different. Okay. Now, the clocking methodology, we need a clock, okay, because we are going to implement a sequential logic here. Every time we are using registers or we are using memory, we need to indicate when the write will take place. So notice that the clock is connected. So for example, if I have register 1 here and I have register 2, so register 1 is provides the input to a combinational logic, and register 2 is at the output of the combinational logic. Notice that we are connecting the clock to both register 1 and register 2. Okay, so notice that we are using edge-triggered clocking. That's the assumption here, edge-triggered clocking. Now these are implemented, these registers are implemented using flip-flops. So the register can only contain a small number of bits, whereas in the case of memory, it's a large number of bits, so it's a different type of technology. So, so at the edge of the clock, okay, so we can use the rising edge or we can use the falling edge. In this example, I'm using the rising edge. If I would like to use the falling edge, there will be a bubble. Okay, so the clock input will be inverted. We write here a small bubble, an inverter, at the clock input to indicate that we are using the falling edge. So here we are using the rising edge. It means that both register 1 and register 2 will be both updated at the same edge of the clock. So the combinational logic, what it does is that it does the computation. It produces its output during a given clock cycle. So during the clock cycle, the combinational logic is going to produce whatever output it's computing. And then at the edge of the clock, we update register 1 and register 2. So register 1 provides the input to the combinational logic, and the combinational logic provides, okay, so the output of the combinational logic becomes the input to the register 2. And therefore, both are going to be updated at the same edge of the clock. So we are using here edge-triggered clocking, okay, and this allows to a register to be read and written during the same clock cycle. So that's the nice thing about the edge-triggered clocking. So notice that we are reading register 1 and we are writing register 2, but the writing will not take place except at the edge of the clock, the rising edge of the clock. So while we are updating register 2, we can also provide a new input to register 1, and therefore register 1 and register 2 will be updated at the same time. Okay. Now, how do we determine the clock cycle? Usually we look at the data path and we go by the longest delay. So here, for example, if we have a combinational logic between register 1 and register 2, this is just to illustrate how circuit designers determine the clock cycle. So it all depends on the delays. The delays will determine the clock cycle. So we might have here a delay. So we'll have a delay inside this combinational logic, which is shown here in yellow. And this combinational logic might have multiple inputs and multiple outputs. For example, it can be an ALU. This will be a combinational logic. So we can go by the maximum delay inside the combinational logic. So that's T max combinational. This indicates the longest delay inside the combinational logic. Usually there is also a delay inside the register. So this is called T clock Q. This is a delay inside register 1. It's also the same delay inside register 2. So at the beginning of, at the rising edge of the clock, the register 1 is going to change its value. So it's going to receive some input here. And then at the rising edge of the clock, notice that here we have the clock at the rising edge, there is a delay inside the register. So at this rising edge here of the clock, okay, the output will not change instantaneously, but it's going to change after a certain delay. This is the delay inside the register. Okay, so we call it T clock to Q. So from the clock edge until we get the Q output. So the Q here is the output of the register. It's the same thing like the Q is the output of a register. Okay, the same is actually the output of a flip-flop. We are using it here as the output of a register. All right, so once we get the output of register 1, it becomes input to the combinational logic. There is an added delay, which is, this is the delay inside the combinational logic. So we go here by the longest delay. So this is T max combinational. And then once we get the output, okay, of the combinational circuit, so all of this should be done during the same clock cycle. So once we get the output of the combinational logic, we have to wait before the next edge of the clock. So this is now the next rising edge. This is used to write register 2. So the output of the combinational logic must be present and it must be stable. And it cannot really be changing. You cannot really have one bit changing from 0 to 1 or from 1 to 0. So therefore, we say that the input is present and it is stable. It does not really change before the arrival of the next edge of the clock cycle. So before the arrival of this writing edge, so we call this the setup time, TS. TS here is the setup time. So we must ensure that the input to a register must be present before the arrival of the next writing edge of the clock. And it must be present before this setup time. So that's the setup time. It's a requirement of register to ensure the correct operation of a register. And the same input must hold. So there is also a holding time, which is called TH. TH here is the hold time, and it means that the input must hold even after the arrival of the writing edge. So therefore, the input does not change, okay? It does not change during this time. So between the TS and the TH must both hold. So therefore, the input cannot really change, and it's going to remain stable even after the arrival of the edge of the clock. Now, what's important to us is the T clock to Q and also T maximum combinational and TS. So TS here is the setup time, that's TS, and TH is the hold time. But the hold time means that the input of a register must hold after the arrival of the clock edge. So this is after the arrival of the clock edge. And this is typically ensured, okay, because the register 1 is not going to change during this time, so it's going to hold. So therefore, the same thing here, the output of the combinational logic is going to hold. So for this reason, the hold time does not appear in the equation. So what appears is that the clock cycle, T cycle here, must be greater than or equal to the clock to Q. This is the clock to output delay in the register, the maximum combinational delay inside the combinational logic, for example, if it was an ALU, and also the setup time. Okay, so this is how we determine the clock cycle. So if you would like to use a faster clock inside the CPU, you have to reduce the delays. If the delays are long, this will slow down the clock. So this is all part of circuit design, and reducing the delays in the circuit design means that we can use a faster clock. Okay, any question about this?
Doctor?
Yeah, we'll come back to this point when we compare the single cycle versus the pipeline versus multi-cycle. I will show you the performance, okay, of these CPUs and how we can compare them. And this will be much clearer later when we compare, okay, these different designs and we see how we can achieve higher performance by improving the clock. Yes, تفضل.
There is a clock cycles inside the combinational logic, right?
No, combinational logic does not use the clock. Combinational logic, you provide the input and you get the output after a certain delay. And the delay is determined by the gates which are used inside the combinational logic. So this delay, the delay can vary from one output to another output, but we go by the maximum delay at any output. So you can look at the delays at all the outputs, and you go by the maximum because you have to ensure that all the outputs have been produced by the combinational logic. Is this clear, Ali?
Yes.
Okay. So there is no clock which is connected to the combinational logic. The clock is connected only to the register because we use the clock to synchronize the right operation. That's the importance of the clock. And we cannot write except after producing the output of the combination logic and after ensuring that the output is present at the input of register 2, and this is present before the arrival of the next edge of the clock. So this is why we have to take into account the delays in order to determine what should be the clock cycle that can be used in a given CPU or in any given digital system design. Okay. Fine. So there is also a clock skew. Okay. So the clock skew here, it arises because the clock signal uses different paths with slightly different delays. So people today, okay, in high-speed circuits, digital systems or digital circuits, what they take into account also the wire delay. Okay, so this is more low-level design, circuit design, but I just wanted to mention this. Okay, so if you look at the clock, notice that the same clock wire is connected to register 1 and to register 2. And in a large design, you may actually have hundreds of registers inside the CPU. Okay, and therefore it's the same clock which is connected to all of these registers. And because we have a wire which connects the clock to all of these registers, the wire itself has a delay. And because the wire has a delay, you might not really get the same edge of the clock. So when the clock goes from 0 to 1, so the rising edge of the clock might not appear at the same time at the input of all of these registers, especially when we have a large design. So this is the meaning of the clock skew. You might actually have slightly different delays, okay, in the clock signal itself, and therefore the edge of the clock, the rising edge, does not appear exactly at the same moment in time at the clock input of all of these registers. So there is a small difference in time, and this small difference is what is called the clock skew. So notice that we add the clock skew, okay, to determine the clock cycle. So we increase slightly the clock cycle to take into account the clock skew. And of course, if we balance, okay, the clock delays, yani we know there is a delay inside the wire, but if we try to put the clock somewhere at the center of our CPU, and we use a similar length from the clock, okay, to all these registers. So we assume that the same delay inside the wire to reach all of these registers. So therefore, we can try to reduce, okay, the clock skew to a minimum, okay, by balancing the wire delay, ensuring that although there is a wire delay, but we try to make the wire delay to be the same from the clock to all of these registers. This is actually, today when you are dealing with gigahertz inside a CPU, okay, so for example, when you have a CPU that uses 4 gigahertz or 5 gigahertz, seconds, 0.2 nanoseconds, okay, that's really a very small delay. I'm not sure if the network is slow, but I can see that I'm trying to turn off my camera just to ensure that the sound is clear. So yes, Ali?
No, I just said it's okay now.
Okay. So what I'm saying is that circuit designers today, because they are using a very fast clock, around like 5 gigahertz in some high-end CPUs, So when the clock frequency is 5 gigahertz, you can calculate the clock cycle, which is around 0.2 nanoseconds. So this is a fraction of a nanosecond. And therefore, the wire delay becomes important and the clock skew becomes important. So this is why circuit designers have to take timing into account. So it's not only the logic has to be correct, but also the timing has to be correct in order to ensure the correctness of the operation of a digital circuit or a digital system. Then you have to take into account not only the correctness of the logic, but the correctness of the timing, okay? Anyways, okay, so I mentioned here the clock skew. Again, I don't really want to go into a lot of details about this because this is low-level circuit design.